Yes. All right, so yes, here we are, Tuesday, October 13th, 2020. We are going to do a little review of displaying categorical / quantitative variables, and then we're going to finish section 1.3 with standard deviation. It's kind of where we left off last week. We didn't really get to do much with standard deviation. I just introduced it and showed you how to find it on your calculator. We're going to actually talk about what that is today and how to do it by hand. I will caution you, you really only want to do this by hand when you have very small data sets. Large data sets, this is unreasonable to do by hand. You will use a calculator. All right, so let's do this. Sticky, there we go. All right, so one thing when I was doing grading on I think Thursday, I was looking at the submissions for the histograms on the quiz, or on the CYU. And one thing that I noticed was that sometimes you guys had actually created something that looked more like a bar graph rather than a histogram. And in one of the discussion boards, many of you said that a bar graph could be described as being skewed. So I want to address these two things to start here. First, a bar graph versus a histogram. Most of you guys already understand that a bar graph is used specifically for categorical variables, and a histogram is used for quantitative variables. Right? That's the main distinction. Right? On a bar graph, the horizontal axis shows categories. Like in our example down here, we have a field of study, and these are categories. Well, a histogram shows the range of possible values for the variable that we've measured. Right? So again, on the two graphs that we have right at the bottom, I know they're small, but we just kind of need to see that there's values there, right? We have numbers actually along the bottom, and it's like a number line, right? It's like a traditional x-axis where we're starting with a number and we go through to the next number. I don't jump, I don't skip numbers. There's no space in between, right? On a bar graph, there's space, right? I provide space between each bar because they are separate things. Right? The y-axis shows the frequency, right? And the y-axis shows the frequency. That's the same between both. The y-axis serves to show the height of the bars. In a bar graph, it's typical for the bars not to touch. Right? And in a histogram, the bars should be touching. They should not have space in between. And then as far as shape, because histograms have to follow order. We go from smallest value on the left-hand side of the graph to the largest value on the right-hand side, and it must be done that way. I can't rearrange the numbers. There's a distinct shape for histograms. They have a very specific shape, and it cannot be different, right? It is exclusive to that distribution. It has that specific shape. In a bar graph, we cannot describe it with shape, whether it be symmetric or skewed to the right, skewed to the left. None of those apply to a bar graph because a bar graph could be rearranged. The way that this graph is drawn, yeah, it looks like it's skewed to the right, but I could rearrange and jumble the field of study so that it looks symmetric. And I could rearrange and jumble it in the opposite direction, right? And then make it look like it's skewed to the left. But I haven't changed the data, I haven't changed the values. Nothing has changed, I've just decided to display it differently, right? This whole distribution for the field of study over here on the bar graph would look different if I arranged the field of study alphabetically. I'd have an entirely different looking graph, right? So that's the main reason why I cannot describe a bar graph the same way as I describe a histogram, right? A bar graph, I can just compare the values. I can say, hey, oh, you know, most people choose business as their field of study, right? In a histogram, I can describe the shape. I can talk about the center, right? I can talk about the spread. We can do standard deviation, variance, all these other types of things. I can have, I can talk about just by looking at the graph. And so that's a huge distinction between a histogram and a bar graph, and it's the main reason why I cannot describe a bar graph, is because the shape, center, that kind of stuff, there is no spread, right? There's no values along the x-axis. I cannot use the same thing to describe a bar graph. So I wanted to make that clear. Those are some common misconceptions that I saw in some of the work that I graded. Are there any questions about the difference between a bar graph and a histogram? All right. Does anyone need a moment to write any of the stuff down that is on this particular slide? Okay. All right. So then, I was saying, I want to briefly talk about stem plots. One of the examples, one of the questions that we had to do with a stem plot, and which numbers, like this is on the CYU, what numbers would be used on that stem plot. Right? Stem plots are like number lines. You cannot skip values. Right? So when we're looking at like this example, which we've seen before, right? Stem plots are used for quantitative variables. Right? We're talking about pairs of shoes. Right? We can use it to compare different groups, different categories that have that same quantitative variable. The stem represents the number of, it could be tens, hundreds, thousands, etc. It just needs to be specified within the key what it's representing, or how to read the number. The leaf represents the second digit, or another digit of the number. Right? The key is needed to read the stem plot and interpret the values. Numbers cannot be skipped in the stem. Right? So in this middle example here, the second one, right? We don't have values that go along with this second one, but I don't skip it. And same thing with the second two and the first three. Even though I don't have values for that, I cannot skip it. Right? It'd be the same as saying, oh, well, this number just doesn't exist because I didn't use it. That's not true. That number is still there. Just like in a number line, even when you're doing like a dot plot, you don't skip the numbers you don't use. Right? This follows the same rules. You have to start at the lowest number and get to the highest number, and you cannot skip the numbers in between for the stem. Now with the leaves, yeah, obviously if there's no value for that spot, you skip it, you leave it blank. But the stem follows the rules of like a number line. I cannot skip values. Okay, and that was the main kind of, I think, reasoning that caused you guys from week 6, I think. I did not grade week 7 CYU yet. All right. What questions do you guys have? Is there anything I can clarify with the stem plot? Okay. Yes, Stephanie.
So just to, because I was kind of confused on where, like, for 0 and it has like different numbers, like 4, 5, 5,
Right.
is how many zeros there are, or is that the amount of?
So that's what we need the key for, right? So the key tells us for this stem plot here, we'll look at stem plot A. 2, 2, or so like this blue, the blue numbers here, right, represents someone with 22 pairs of shoes. So in this case, the stem represents how many 10s I have and then how many 1s. So in our data set, right, for this stem plot here, if I were to like write out all the numbers represented in this row, that would be 4, right? It's essentially just 4, 5, 5, 5, 6, 7, 7, 7, 7, 8, and then we have 10. right? The next row, we have 10 4 times. So we have a 1 and then 4 zeros. That means I had 10 show up 4 times. And then 11, 12, 14, 22, 35, 38. So this, the string of red numbers here, that would be the data set represented by stem plot A.
Okay, that makes more sense now. I
Okay.
got it. Yeah. Thank you.
And then the one stem plot B, this is called a split stem. Right? So instead of doing all of the ones without tens, like the 4, 5, 6, 7, 8, 8, you split them in half. And so 0 to 4 goes in the first row for that stem, and then 5 to 9 would go in the second row. 0 to 4 in the first row, 5 to 9 in the second row. So it helps kind of split it up a little bit so you can see the distribution a little easier. And then we have the back-to-back stem. That's a back-to-back split stem. So there's a couple different variations on the stem plot, but they all follow that same rule with the stem and how to read the numbers. And you can play around with it. Like if you have large numbers, you can kind of change how to read the numbers using the key. But that's kind of up to you. And really, with really large numbers, you're probably not going to use a stem plot unless there's not a whole lot of values. Right. Any other questions? Those are really good questions. Thanks for asking. All right. So then next, something else that I observed is just like writing. I know this is not an English class. This is a math class. However, what you write and how you write it matters. All right? The graders will care about how you write your answers. You need to be specific and write with good grammar and overall structure. Right? These are the people who grade these are like college professors or people who have been teaching AP Stats for like 20 years. They don't want to read poorly written work. Okay? I know that sounds petty, but it's just that could influence how they grade. You could have done all the right work, but then you don't write it out well, and you may not pass because of it. So I kind of have to like push you guys to write properly. You know, and I stress on this because this happened to me when I was doing a major assessment in college that basically determined if like I could get my teaching credential. All my work was done very well. I was considered a very good top candidate, but I did not pass my exam because I didn't write well enough. I literally had to just go back through and add fluff and make it sound prettier to pass. All of my content was excellent. All of the things that I said were the right things to say. I just didn't say them well enough. So I had to go back in, pay another $300 to take my exam again, and then I passed. Right? So this is very personal to me. I understand it can be frustrating and unfair, but it's just the way the system is. So I need to prepare you guys for that. Right? So you have to, again, what I'm saying, say what you mean. Right? Don't leave things up to interpretation. Right? So we have these two sentences here saying essentially the same stuff. Right? The first sentence says the range of the numbers is 8. Excellent. What numbers? Right? And then we have something that's more specific. The range for the height of the players is 8 inches, and all the players' heights are between 68 and 76 inches. It's conveying essentially the same information, but now we've given specifics. We've written a nice sentence, providing details, right? So the second sentence is considered a better answer. They both essentially have the same information, but one is considered better than the other. So you have to consider that when you're writing your answers. And with me, it's practice. You're practicing how to write these things well. Then the other thing that I saw within some of our written responses is using normal versus symmetric. This is a issue with the previous math classes and the way that those authors chose to write that text. Only special distributions are normal. They have to meet certain special criteria to be considered a normal distribution or approximately normal distribution. If they don't meet those criteria, they're just symmetric or approximately symmetric or roughly symmetric. So for now, when we're describing these things, we want to say that they're symmetric. Once we've gone over what a normal distribution is and what needs to happen to call it a normal distribution, we can start using that verbiage in the proper circumstances. But for right now, we can't use it. It's not proper to use it yet. So things that look like they could be normal, we're just going to call them symmetric for right now, because we don't have the rules for having something be approximately normal yet. Okay? What questions do you guys have about this? Again, you just need to keep in mind writing, even though it's a math class, how you write your answers when you're writing out like your paragraph of description of a distribution. You should write it like you're writing it for your English teacher. It should use that kind of grammar and structure and specifics and things like that. All right. Next, we're going to get into our standard deviation. All right, so I'm going to switch gears here and go into OneNote. Excellent. All right, so here we go. We have our standard deviation. This is the same definition that I gave at the very end of the lesson last week. I know it was a week ago. So here it is again. Another way of measuring spread is using the standard deviation. Right? Standard deviation and variance measure spread by looking at how far the observations are from their mean. All right, so we have to find the mean, and then we basically measure, okay, how far away is everything from the mean? And that's what we're measuring. What's the distance from our average? How far off are things? All right. So we have this crazy definition, right? Standard deviation, S sub x, right? Measures the typical distance of the values in a distribution from the mean. It is calculated by finding an average of the squared deviations and then taking the square root. This average squared deviation is called the variance. The symbol of the variance is S sub x squared, is given by this crazy formula, which basically says, right, starting here, x sub 1, which is our first term, minus the mean squared, plus the second term minus the mean squared, plus the third term, plus all the way plus the nth term minus the mean squared, all divided by how many terms I had minus 1. Okay, so we're going to go through a process that's going to help this make a little more sense and actually kind of like break it into pieces. So we don't necessarily have to, we're not going to write it out like this in this formula that's all kind of got a bunch of letters and stuff, to try and make a little more sense of this. Standard deviation is given by this other formula, which is we find the number here, we find the variance, and we take the square root. Okay? And the only reason there's an x with the s is because in this example, in this definition, X represents the variable we're using for our observations, X. We could have another set of data and label it Y. We could have a third set of data and label it Z. And we'd have S of X, S of Y, S of Z. It's just a placeholder representing that specific data set. Okay? Any questions on what any of this in the formula represents? Okay. So we're going to look at this example. Right? So right here we have low is the number of pets owned by 9 children. They have already been arranged from lowest to highest. Right? So we have 1, 3, 4, 4, 4, 5, 7, 8, and 9. We're going to use this data to practice finding standard deviation. All right, so we're going to start by making a number line and making a dot plot so we can kind of see a visual representation of our data. There's not a ton of data points, so it's not too horrible. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. I need to write the 8 there. 9, and we'll use red, why not? So we have a dot here, nothing at 2, 1 at 3, 3 at 4, 1 at 5, 1 at 7, 8, and 1 at 9. All right, so we have a quick visual representation of our data. Okay. Now, we need to find the distance, essentially, from the mean, which means we need to find the mean first. Right? So let's find our mean. It's something we need. So x bar, that's going to be 1 plus 3 plus 4 times 3 is 12, plus 5, plus 7, plus 8, plus 9, all divided by 9. 16, 21, 28, 36. I think that's, oh, no, that's 45. What a goober. That's not 47, that's 45. 45 divided by 9 is 5. All right, so that means five right here, that's our mean. It is also, we could say it's our balance point. All right, so we're looking at distance from the mean. So what we're going to do here, we're going to make a basic table. We're going to say, okay, we have an observation, and this is the fancy word for the numbers that we have in our data set. Then we have the distance from the mean, and this last one is going to be distance from the mean squared. Okay? These are the numbers that I need to find the variance and then find the standard deviation. So we have 1, 3, 4. And I'm not going to write 4 the 3 times. I'm just going to like make a little note here. There's 3 of these. Right? This is maybe not the proper way. Like, if you really want to show all the work, you'd want to list all of them, but for the sake of time, there's 3 of those same ones, the same distance and the same distance squared. So I don't necessarily need to show it 3 times. You get the point. We have 5, 7, 8, and 9. All right, so if we're looking at 1, right, 1 has a distance from the mean. 1, 2, 3, 4 units, right? That's the distance. Distance isn't measured necessarily positive or negative. We could calculate it that way. We can say 1 minus 5 will get -4, and squaring it turns it positive. That's kind of one of the reasons why we square all the numbers, right? So we have 1 minus 5, that's going to be -4, and then -4 squared, 16. We have 3 minus 5, right? That is -2. Again, we can see from 3 to 5, we go 2 spaces. We're left 2 spaces, right? We have -2 squared, 4. 4 minus 5, -1. -1 squared, 1. And so what we're doing right here is the top of our division from the formula. We just haven't added them up yet. We're just finding out what all those numbers are that we're going to add up and then divide by 9 minus 1. 5 minus 5, 0, 0. 7 minus 5, 2. Squared is 4. And next we have 9 minus 5, 4. All right. So we have all of our kind of distances from the mean and the distances from the mean squared. Right? So now, we're looking at how to find the standard deviation now. The steps, we've done step 1. Find the distances of each observation from the mean and square each of these distances. All right, cool. Step 1 is done. Average the distances by dividing their sum by n minus 1. Okay? We have n minus 1. So now we got to add these numbers. Switch to... So now we're finding that big. As far as our formula goes, right, we have s sub x squared. We're going to have 16 plus 4 plus, and remember I have 3 of the 4s here. I'm going to say plus 3 because 3 times 1 is 3. Plus 0 plus 4 plus 9 plus 16. And we're going to divide this by n minus 1. 9 minus 1. This is when we get our Indian calculator and add some things up. Yeah, 52 divided by 8. We get 6.5. Right. This number here, this is what's called the variance. All right. So we have our variance now. And standard deviation is the square root of the average squared distance. We'll do that right underneath here. So we'll have now loop, right, just the s of x, and that's going to equal the square root of 6.5, which will give us not a very friendly number. 2.55. All right. So the standard deviation essentially is telling us that on average, our measurements here in our dot plot or in our distribution observations are about 2.5 units or 2.5 pets away from the mean. That would be one standard deviation. Okay, and so that's the standard deviation is another way of measuring how spread out these things are. So the larger the standard deviation, the more spread out our numbers are. The smaller, the more close together they are. Right? Same thing goes with the variance. The larger the variance, right, the more spread out we are. Smaller the variance, the less spread out we are. Right? These measurements depend on the mean, right? Using the standard deviation and variance are dependent on the mean. Our, IQR, quartiles and things, those depend on the median. So they both are using a separate measure of center to determine how spread out stuff is. Okay? So it's kind of like we have these two different strategies depending on the measure of center that's being used. All right. What questions do you have? Questions? All right. All right, so you have it. Does anyone need another moment to write anything down from this mess of math? Yes, okay. I shall wait. Have some coffee. All right, and so just like we can use like the IQR, right, to find out if something is an outlier, there is a kind of general rule on using standard deviation in the same way, right? And we can find outliers using the standard deviation, or one method of using the standard deviation to find outliers. Oops, easy. Is if something is more than 2 standard deviations away from the mean, we can consider that point an outlier, those points if there's more than one. So if there are more than 2 standard deviations, this would be 2 standard deviations to the right of the mean, 2 standard deviations to the left of the mean. Just like when we do the IQR times 1.5, we add it to Q3 and we subtract it from Q1. Same idea with standard deviation. We're going to add it to the mean 2 times. We're going to subtract it from the mean 2 times. Anything that's outside of that 2 standard deviation bubble could be considered an outlier. Okay? So again, it's kind of like the magic number is 2 standard deviations. There are some arguments saying that this isn't a great measure of finding outliers, but it is something that we should be aware of. There's many different ways of trying to determine outliers. We're only going to cover a couple of them. So if we consider this idea, 2 standard deviations away from the mean with our example here, right? The mean was at 5. If I add, let's just go with 2.5. So I add 5, 2.5 and 2.5 is 5 to 5, right? That would essentially make the cutoff at 10. We don't have anything past 10. Subtracting 5 would make the other cutoff over here at 0. So anything greater than 10 or less than 0 would be considered an outlier. We don't have those in this data set, so we can say that there appear to be no outliers in this data set, right, for the number of pets owned by these 9 children. Added here 2 standard deviations. So the more I add, the worse it looks. Okay. Anything I can clarify? All right. Excellent. So now we're going to jump back to this. All right. So this one. Last thing I wanted to kind of briefly go over is this little blurb from the book. It says how to organize a statistics problem before step process. All right. You need to state, plan, do, conclude. Or set. State, what's the question you're trying to answer? All right. This is super important. Some of you, many of you have made the mistake in this class and probably in other classes of answering the question that wasn't asked. This is very easy to do. You can look at the stuff and start answering things, look at your data, look at the question, and answer stuff that wasn't necessarily asked, or answer the question improperly, right? So the first thing to do is simply identify what's the question you're trying to answer. Plan, how we go about answering the question. What statistical techniques does this problem call for? Do we need a bar graph, a pie chart, a histogram, a dot plot, stem plot? What's going to be the best thing to represent the data? Do I need to make a table? Do I need a marginal distribution, a conditional distribution? what are the things necessary to compare the data from comparing data sets? Right? What things will you need? How we go about answering the question. Right? Do make graphs and carry out needed calculations. Right? And then conclude. Give your conclusion in the setting of the real world problem. And again, this comes down to that written part. Right? The plan and the do is just the steps needed so that you can get to that written paragraph, so to say, at the end, where you're giving your conclusion based on all the data and work that you've done. Right? It may need to have your description of shape, center, and spread, and possible outliers or unusual aspects. If you're talking about quantitative data, it definitely needs to have those 4 things. So, your conclusion needs to answer the question, right? Whatever question you were trying to answer, your conclusion needs to contain the answer to that, and it needs to be supported by the data that you just worked with the things that you made. You need to be able to refer back to the graphs that you made, the calculations that you have. How do they work to support your answer? And you have to write that conclusion. Right? So, there's an example of this state plan do conclude in the textbook. It's on page 65 and finishes on page 66. And it's who texts more, males or females. That would be a good thing just to kind of read through to see how the textbook shows like a full, complete process with a nicely written conclusion and all that stuff. Yeah. So I wanted to show that. And last but not least, well, first, does anyone need a moment on this page for any reason? Please raise your hand. Okay, so then last, we will, see if I remember to do and that. We're gonna go to Canvas this morning. All right, so in Canvas here, in our modules, we have week 8. It's almost entirely done. The only thing I need to make is we will be doing our next self-assessment. It's being signed this week because we are finishing chapter 1 and moving into chapter 2. So there will be a chapter 1 self-assessment that I will hopefully have ready by tomorrow. I should have it ready by tomorrow, so you guys can start working on it. And kind of like the last one, this will be due not like the other assignments that are normally due, like by, or due, I say, suggested to be done by Monday before class. On Tuesday, this you'll have until next Friday as far as like time to work on it. All right. So this has a little bit more of an extended time to work on it than our typical weekly assignments, but this does take the place of the quote unquote like weekly CYU or weekly assignments. It will be the self-assessment. Remember, the self-assessment is worth more than like the weekly assignments. It's got a higher weighting to it, right? So if you're choosing things to do, choose this one. Right? If you want to do some assignments, this is the one you need to make time for. It is worth more. Okay? So there's that. Our discussion boards, both the discussion boards for this week are already ready and available. Unless you're really familiar with percentiles and those types of things, I don't really suggest jumping into this one yet. We'll talk about that stuff on Thursday. I'll be posting this live class session to Canvas later today. And once again, I do have videos for chapter 1. I will most likely be making one about standard deviation. And if there's anything else you'd like a video on, please let me know. I will take requests. If there's things you'd like to see examples worked out or given, you know, better explanations for, just let me know. I'd be happy to make a video. If you want it, probably someone else does, and that'll work out for everybody involved. All right.